Hello, Standoff. I would love to invite our next bunch of speakers, a duo of speakers, I understand. That's Doina, Cosovan, and Katarina. They are going to tell us about the horrible dangers awaiting developers of advertising for mobile devices. I guess they're much better equipped to tell you about what they've got to tell you, so please stay tuned. It's gonna be very interesting.
We are model researchers at Security Scorecard, and our presentation is about hidden risks of advertisements. This research was first time presented at the Virus Bulletin conference this year in October. As you probably all know, advertising is almost everywhere. We can find advertising in mobile applications and mobile games, also on websites, for example, so-called websites with free content, and also on YouTube, Facebook, Google search results, and so on. To get an idea of how advertising world is structured, we have ad networks, for example, Uplovin, AdMob, AdColony, and so on. And an ad network gets their ads from their clients, and it displays them on their network, and it will get paid by their clients. An ad mediation platform, for example, AdMob, IronSource, and MobUp, it's a new type of product that integrates multiple ad networks in their product. And that way, their clients can use multiple ad networks using only one SDK. To get an idea of how big this advertising world is, we know from Verizon Media Native ad network website that they state that they have close to 1 billion monthly active users. This means that they have a huge number of users, and also this means that they have to take considerable security measures in order to protect their users. We found various Sinkholing opportunities relating to advertising world. We are going to present most interesting 5 cases that we found, and we separated them in 3 categories. First category is about expired hard-coded domains. This is most prevalent category. For example, it can happen when a company ceases to exist and their previously owned domains no longer get renewed. And in this case, those domains may be available to buy, and they can still be used by various applications, for example. The second category is about using usage of wrong domains, intentionally or unintentionally. For example, an unintentional case is when someone makes a typo and distributes that domain with a typo to an SDK, or maybe the SDK owner makes a typo when he adds a particular domain. And the third case is about available generically generated domains, so-called DGAs, when, for example, an advertising entity is using domain generation algorithm in order to have a backup to the main communication domain. So that in the case that that domain gets blocked, for example, by an ad blocker, they still have connections to their servers by using this backup that generates different domains by day or by month. So it's more complicated to block it. As an agenda, we'll present more details about these 5 cases, and we also have an interesting demo when we show that we were able to display a custom ad, and all it needed was an application, mobile application, knowing the communication protocol, and the possibility to use a domain that was available to buy. And at the end, conclusions as usual. First use case is about an expired hard-coded domain that belonged to an advertising SDK. This domain was used only by close to 40 Android applications, not a big number, and most of them are related to gaming. But what is interesting is that only for 40 Android applications we received a request for more than 500,000 unique IPs daily. So it is a considerable number of devices that are using those mobile applications. As a country distribution, we have US in the first place with close to 1/3 of those IPs. Then we have Philippines, Brazil, India, Great Britain, and China with only 4.2%. So this looks to be something more prevalent to US. This is an example of a GET request that we were receiving. We noticed this application package embedded in the request. This is how we were able to make a statistic of approximately how many applications were using this domain or SDK. This is an example of a post request from the same domain, and it also provides a JSON embedded data that specifies an application package. It's not too much information sent here, but we're able to do some statistics related to the number of applications using this particular domain. We assume that in this case the main company that owns this domain ceased to exist, and they no longer renewed that domain, and that's how those applications were still using that domain, and they didn't update to some new version of the application. The second use case is about also a hard-coded domain that expired. It's about a multi-platform advertising SDK. Its interesting part is that it was contacted by more than 10 million unique IPs per day, and 70% of those IPs are located in the United States. From the statistics that we were able to make, we found out that it was used by more than 10,000 websites, most of them related to news and social media, and close to 2,000 Android and iOS applications, also most of them related to news and social media. By this time this problem is solved, and we are no longer receiving requests, but it was a problem for a few months. As a distribution, we have US on the first place with close to 70% of those requests. Then you have Brazil, Taiwan, Canada, Great Britain, also Spain and Germany, other countries from Europe. Even if this, for example, Germany has 1.5%, this 1.5% means close to 100k IPs per day. So it's not quite insignificant on that large scale. This is an example of a request that we were receiving for this particular case. From the referrer field, we are able to extract some statistics about the websites that have used this particular domain. And we also have the user agent that's usually present on HTTP requests. And for related to mobile application statistics, we had this type of request where at the end was an is requested with field that had a mobile application name there. So that's why we were able to also do some statistics about mobile application that were using this type of service. As I mentioned, this problem is solved now. It was a problem for a few months, and what we think what would happen was a company also ceased to exist and was using this domain, and we think that somewhere some SDK didn't update to remove it, and it was still used by a big number of devices. But the problem, meanwhile, was fixed. The first use case, the third use case is about unintentionally used wrong domain. In this case, advertisers bought the correct domain, but distributed somewhere was distributed a wrong domain with a typo. We know that it was a typo because it looked like a typo, and after we fixed the typo, we found out what was the real intended domain that was already bought by the advertisers. And it was a company that was relatively new. They looked to be still in development. And from the request that we received, we had close to 2.5 million unique IPs per day. And because it was a Russian-specific domain, as expected, 90% of those IP addresses were located in Russia. And also we are able to do some statistics, and that domain was used by close to 20k websites, mostly of them related to gaming and movies, and close to 1,000 mobile applications. The good part is that the problem was fixed in a little over a week. We were able to find out what was the advertising entity that was supposed to use that domain, but we didn't find a way to contact them. But they figured out in almost a week, and they fixed the problem shortly. So that's the good part. As a country distribution, as expected, Russia was on the first place with close to 90% of those IPs. And this is an example of a request that we were receiving in that particular case. And from the refer here field, we were able to extract those website statistics. The fourth use case is also about an intentionally used wrong domain, but this was intentionally used wrong domain, and we assume that it was in order to evade some possible syntax errors. It was about an HTML5 advertising player. Also was something specific to Russia, and it was a list of advertising domains, and at the end they added a domain that was looking more like some random keystrokes on the keyboard, and was not meant to be contacted unless some rare conditions were met. And it happened that those conditions were met at some point in time. And after we were able to sync all those domains, we received requests from 500,000 unique IP addresses. And the problem was really fast fixed, like in 2 to 3 days. Probably took so long because it was over the weekend. And it was also easy to fix it, as if they only had to change a domain in some JavaScript code. It was not like fixing a problem in a mobile application. This is a snippet of the code before the fix. We have some links to advertising entities, and they were using AND as a separator. They had some strings, they concatenated those strings, and those strings were separated by AND. And here was a list of like 20 to 30 advertising links that they were using. And at the end, they added a domain that was like a random domain. And we assume that this domain was added here so that when they splitted this big string by end, everything worked okay. So this was before the fix, and it happened that this domain started to be contacted because less than 5 advertising links before the last link were working. So this is a particular case when this domain could have been accessed. And what they did after the fix was to replace that domain with a domain that they owned and they could control. So that problem was no longer present. So this is before the fix, only the difference is the last domain, and after the fix they replaced the domain at the end of that list with a domain that they own. So the good part is that we fixed it fast. We didn't even have time to find out a way to contact them. We didn't even identify who should have contacted in that case, and they already fixed the problem in 2 to 3 days. This is an example of a request that we were receiving. We think that this was a serious problem because both that link was or domain was intended to display advertising on various websites. So it was a big security problem because someone could have displayed whatever they wanted, or they could have used an exploit. Also, it was displaying video, that HTML5 player. And we're not able to extract statistics because the problem was fixed in fast. Next, I will invite Doina to continue with an interesting demo and also with the most interesting case related to using an domain generation algorithm.
Use case number 5 deals with an advertising mediator. In order to understand what an advertising mediator is, let's first go over the relations between various personas that are part of the advertising industry. Everything begins with a seller. When a seller wants to advertise his product, he contacts an advertiser and asks the advertiser to show his ads to potential customers at a cost. Of course, there are multiple such sellers and advertisers, and each seller can use multiple advertisers, while each advertiser can be used by multiple sellers. However, an advertiser doesn't contact potential customers directly. Instead, he develops a software development kit, shortly called an SDK. The SDK is embedded by developers in their applications or websites. The users of these applications and websites are the ones that are actually shown the ads. Usually, a developer uses multiple advertisers, which means that he has to integrate multiple SDKs in his application. The purpose of a mediator is to simplify the relationships between advertisers and developers by mediating multiple advertisers in a single software development kit. In this way, a developer can integrate a single SDK but use multiple advertisers. As I already mentioned, our fifth use case is a mediator. We are not going to disclose its name, but I will tell you that it is developed for multi-platform mobile devices and integrates approximately 70 different advertisers. The interesting part about it is that it borrowed a technique from other developers. This technique is the usage of a domain generation algorithm, shortly called a DGA. A DGA is an algorithm that usually uses the current time as a seed in order to pseudo-randomly generate domains to be used for a short period of time. This particular mediator tries to contact 4 different domains every day. First, it tries to contact its hard-coded domain. Next, it tries to contact the domain generated for the current year. This domain is obtained by using the current year as a seed for the DGA. Thirdly, it tries to contact the domain generated for the current month. This domain is obtained by using the current year and month as seeds for the DGA. And lastly, the domain generated for the current day is contacted. This domain, as you might expect, is obtained by seeding the DGA with the current year, current month, and current day. Since the DGA used by this mediator acts as a fallback mechanism for its hard-coded domain, we suspect that the mediator developers use the DGA in order to avoid ad blockers in the same way in which malware developers avoid blacklists. Let's see how this works. Here we have 3 entities: the mediator, the advertiser, and the user. The user operates a device that is running an application that contains the mediator SDK. In the case in which the hard-coded domain is accessible, the domains generated by the DGA are not important. Let's see why. The device contacts the hard-coded domain, which belongs to the mediator. The mediator responds with the URL of an advertiser. Then the device contacts the advertiser's URL and receives an advertisement to show to the user. Everything works as expected for all the involved parties, and the generated domains are not used at all. In the case in which the hard-coded domain is not reachable and the generated domain belongs to the mediator, the workflow is only slightly different. What happens is that the device tries to reach the hard-coded domain. Since it can't, it tries to connect to the generated domain. because the generated domain also belongs to the mediator, the device ends up contacting the same entity and receives the location of an advertiser. Upon contacting the advertiser, the device receives an ad and shows it to the user. So the generated domain acts as a backup for the hard-coded domain. The problem is that the mediator doesn't own all the generated domains. This means anyone can register and use its generated domains. We sinkhole domains generated by this mediator's DGA. And even though the sinkhole is only contacted when the hard-coded domain is not reachable, we still receive requests from tens of thousands of unique devices daily. The requests are mostly coming from Russia, United States, and China. Since the requests are meant for the mediator, they contain information about both of the mediated parties, sellers and advertisers on one hand, and users and developers on the other hand. The information about the devices that is included in the requests contains both hard-coded and software characteristics. Amongst the hardware characteristics, we observe the device manufacturer, type, and model, the height, width, and pixel ratio of the display, the total and available RAM, as well as the percentage of remaining battery. While the software characteristics include the platform, the operating system version, the operating system SDK version, and whether the device is rooted or not. The information about users include language, time zone, local time, gender, age, relation, occupation, as well as whether the user is smoking or drinking alcohol. These fields might help advertisers to choose more targeted ads. However, in most of the requests we received, these fields are empty. The requests also contain some statistics about the ads shown to the users. We first specify whether the advertising tracking is enabled, and then specify the number of shown advertisements, the number of fully watched advertisements, and the number of advertisements on which the users clicked. In the request, there is also information about the applications in which these ads are shown. This includes the time at which the application was installed and how long the application has been running. An interesting piece of information here is the application key. This is the token that an application uses in order to identify itself to the mediator. This means that an attacker can sinkhole a generated domain and collect these application keys from the received requests. Then it can use them to impersonate these applications, meaning that the attacker can communicate with the mediator on behalf of these applications. Other interesting fields are the name and version of the package belonging to the applications in which the mediator SDK is embedded. This package name allowed us to figure out which applications are using this mediator. We collected approximately 2,000 different applications. Out of the top 10 applications sorted by the number of received requests, there is one that has almost 1 million installs, one that has almost 500,000 installs, and 4 which have 250,000 installs. After sinkholing this mediator, we started to think about what would happen if the hard-coded domain is unreachable and the generated domain belongs to a malicious third party. Let's see a potential scenario. Imagine the device tries to contact the hard-coded domain and is not able to do so. As we already know, it will try to contact the generated domain. An attacker that registers the generated domain can set up a fake mediator server and reply with the location of a fake advertiser. The device trusting the mediator will contact the received fake advertiser, will receive a fake ad, and will show the fake ad to the user. Therefore, this can be considered an infection vector. We would classify it as a variation of the widely known malvertising infection vector. The difference is that in malvertising, the attackers are using the same channels as legitimate sellers in order to spread their exploits as ads. But in this case, the attackers have a shortcut, because they don't have to go through advertisers and mediators. Instead, they can set up their servers and spread their specially crafted ads. These specially crafted ads might contain exploits installing malware on the devices. Besides being an infection vector, this is also a reconnaissance channel, because the attackers receiving the requests will know the version of the operating system and the version of the operating system SDK running on those devices, as well as which version of which application is embedding the mediator SDK and showing the ad. This allows the attackers to provide an ad that is targeting a particular version of software or operating system running on a particular device. And there is one more observation I would like to mention here. Although we do not encourage users to stop using ad blockers, we would like to mention that in this particular use case, using an ad blocker can be more dangerous than not using one. Let's see why. If the user is not using an ad blocker, the device will be able to reach the hard-coded domain which belongs to the mediator, and the user will be shown real ads. However, if the user is using an ad blocker, then there is a high probability that the hard-coded domain is blocked, while the generated domains are not blocked by that ad blocker. Why? Well, because it is easier to block a hard-coded domain than to extract the DGA and periodically generate and blacklist currently active domains. So what happens if the ad blocker only blocks the hard-coded domain? Well, the device will not be able to contact the hard-coded domain and will try to contact the generated domain, which can belong to a malicious third party serving exploits instead of ads. So this means in this particular use case, using an ad blocker means you might be served exploits instead of ads. We were curious if this communication flow is a realistic use case. So we decided to do a proof of concept. Because we didn't want to actually respond to devices contacting our Sinkhole, we decided to do our proof of concept in a controlled environment. Therefore, we use an emulator running an application that contains the mediator SDK. And in order to have a fake mediator and advertiser server, we are simply running locally scripts that impersonate them. But I believe there was enough talk. Let's go to see the demo. Let's set up all the components for the demo. We will start by setting up the proxy. As a proxy, we use Burp Suite Community Edition. Although an attacker doesn't need to use a proxy, we use it for two reasons. First, because we want to be able to see the traffic between the scripts that we are running locally and the emulator. And second, because we need to redirect the mediator's hard-coded and generated domains. In order to redirect the domains, we are going in the Project Options tab, Connections sub-tab, and here I added the hard-coded domain and I set its IP address to localhost. I did it because we are trying to simulate the use case in which the hard-coded domain is not reachable, so that the mediator SDK can go on and contact the generated domain next. I also added the generated domain and set its IP address to localhost as well, because we don't want the emulator to contact our Sinkhole. We want it to contact the scripts that we are running locally. After adding these domains, we go in the Proxy tab, and in the Options sub-tab, we can see that we set up the proxy to use the port 8888. Also from here we can export the burp certificate. We will be needing it for the emulator. Let's do it now. Let's call it burp.char and save it. We see that it appeared in this folder here. Then we will go in the Proxy tab, HTTP History sub-tab, because here we will be seeing all the communication. Now that the proxy is set up, let's start our scripts. Here I will start an HTTPS server running on port 443 that impersonates the mediator. All the requests meant for the generated domains will come to this script, and this script will respond to the location of the ad server. Here I will start the ad server, which is an HTTP server running on port 80, and all it does is to serve the location of an ad resource. Let's start with two. This is an HTTP server running on port 8000 that will be serving an ad resource, and this resource is actually a security scorecard video. Let's start it. Now that we started all the scripts that we need, let's set up the emulator. In order to set up the emulator, we first need to make sure that it trusts burp certificate and that it uses burp as a proxy. In order to set up burp certificate, we will drag and drop it in the emulator, and then we will go in the settings. Then we will scroll down until we get to the personal section, and we will click on security. Here we scroll down again because we need to get to install from SD card. When we drag and dropped the burp certificate on the emulator, it was served on its internal storage in the download folder. If we go here, we can double click on it in order to install it. We are required to give it a name, and we name it burp. And we are required to set up a pin. Let's do this as well. We need to repeat the pin. And now we can check that the certificate was actually installed by going in the trusted credentials under the user tab and check that the certificate is here. Now that the emulator trusts burp certificate, let's set up the emulator to use burp as a proxy. We need to scroll up. In the wireless and network section, we will click on more. And then we will click on cellular networks, we will click on access point names, and then we will click on T-Mobile US. Here we can set up a proxy. We set its IP address to 10.0.2.2 because this is the IP address that the emulator uses to contact the system on which the emulator is running. Then we set its port to 8888 because this is what we set burp to use. And then we need to make sure that the username is empty and that the password is empty too. By default, they are set to none, but burp is not using these credentials. Then we go and save this proxy. After saving everything, in order to make sure that the changes are applied, we will set the airplane mode to on and then to off. And we are done with the proxy. Now we can go and install the application that has Mediator SDK. In order to do so, we will drag and drop it in the emulator and we will wait for it to be installed. This application starts, and the first thing it does is show an advertisement, and only after showing the ad it lets the user interact with the application. Now we can start the application. We accept the privacy policy, and you are already seeing activity both in the proxy and in the scripts, and we are waiting to see the security scorecard video, which was served as an ad. Here is the video. Now we can stop the emulator because this is what we wanted to see. The application will show the video and then we'll continue what it has to do. Let's take a look at the proxy. We can see that it first tried to contact the hard-coded domain, but it was not able to do it. So it contacted the generated domain, our locally running script, which provided the location of an ad server. Again, our locally running script. The ad server was contacted here, and we can see that it provided as an ad resource the location of our security scorecard video, which we actually watched on the emulator. This is all with the demo, and now let's return to our presentation. We have shown that it is possible for an attacker to register a mediator domain in order to serve specially crafted ads. We contacted the company to tell them about the risks of using a DGA. Unfortunately, their solution was to change the DGA. This doesn't solve the problem, because it is enough to simply extract and sinkhole the new DGA. However, even if the company decides to remove the DGA altogether, it is not enough, because it only means an update to the Mediator SDK. But all those approximately 2,000 applications that are currently embedding older or current versions of the SDK also need to issue updates. And all those users that use those 2,000 applications need to update their applications too. Note that this is just one possible attack. Of course, it is the most worrisome one, but the attackers can do other things as well. For example, they could gather information about users and advertisers in order to sell them on underground market, or they could impersonate the applications in front of the mediator. Since we are at the end of the presentation, let's take a step back and make a summary. In this presentation, we looked closely at 5 different use cases in which advertisers or mediators created a novel infection vector. We did so by letting their domains expire. The use cases are different in terms of the Sinkholing opportunity, the targeted platform, the way in which they can be fixed, and even how prevalent they are. However, these are just 5 examples. What we want to emphasize with these examples is that this happens often, and that this happens for various advertisers and mediators that have huge user bases. The conclusion is worrisome, because the attackers can easily sinkhole advertising infrastructure and use it as a novel infection vector in order to target the advertiser and mediator user base.